Okay, let's take a look at this derivative problem. F of x equals log base 5 of the absolute value of 5x minus 7. See if you can find the first derivative of that right now. If you haven't done so, do it now, please. Press pause. Well, the first thing to remember is we don't have a rule for a log base something else, but we do have a way of converting log base whatever to our standard base of e. And that rule is log base b of a is log of a, natural log of a, over the natural log of b. So I can rewrite this function as the original function as natural log of the absolute value of 5x minus 7 divided by the natural logarithm of 5. Well, 1 over natural log of 5 is a constant, so I start by using the constant multiple rule and bring it out front. I'll do the substitution in my head here. This is the logarithm of the absolute value of u. The derivative of log absolute value of u is 1 over u times the derivative of u. U is 5x minus 7, so this is 1 over 5x minus 7. The derivative of the u, derivative of 5x minus 7 is 5, and we still have our 1 over ln of 5. And so there's the derivative right there. I can check this in my calculator, but I'm going to have to enter the function this way if I've got the older operating system on a TI-84. So I'm going to have to enter it in as, say, as ln of absolute value. Absolute value, of course, ln, there's a button right on the calculator for that. ABS is found under math, right arrow to number, or num, and it's, I think this is the first one. And then put your 5x minus 7 parentheses, close the parentheses for the ln, divide by ln of 5. So that's the original function. Now, if you have a newer TI-84, you can put in absolute value by just using a vertical lines, or it looks like a vertical line here around this, just like you would normally write absolute value. And there actually is a log base 5 you can actually put in as well. So you could do it that way in a newer operating system. But this way it works in the newer calculators on the 84 as well. Put your numerical derivative in y2 as always. Turn off y1. y3 is going to be our answer here, which is 5 divided by ln of 5 times 5x minus 7. Watch the parentheses there. y2 and y3 match in the table, so that's good. Okay, now let's do another derivative. Well, notice that the 5 times ln of 5 could be brought out front as a constant, and then we can think of this other part as just 5x minus 7, the negative 1. So again, with u being 5x minus 7, this is u the negative 1, so it's negative u to the negative 2 du is the derivative. We still got the 5 times ln of 5 here. The negative 1 brought out front makes that a negative. Subtract 1 for the power makes that a 2. The derivative of the inside is 5. That 5 and that 5 makes 25 when you multiply them together. And so you get negative 25 over, well, instead of think of this as to the negative 2 power, you can think of it as 1 over this thing to the positive 2. So the final answer for the second derivative is the opposite of 25 over ln of 5 times 5x minus 7 squared. Again, we can check it since I already had this typed in as y3. I went back and changed y2 to be numerical derivative of y3. Let y4 be my answer here. Negative 25 divided by ln of 5 times 5x minus 7 squared. Turn off y3 and y1 I turn off or delete. It's not needed now. Check the tables for y2 and y4, and sure enough they match, so that's a check. To find the tangent line, first of all, let's just see if it's even defined at y equals 1. Put in 1 in place of here. We get 5 times 1 is 5, minus 7 is negative 2. Absolute value of that is 2, so we get ln of 2 over ln of 5, okay, which is also log base 5 of 2, if we wanted to write it that way. But I'm going to leave it with ln's because that's the easiest way to get it in the calculator for one thing. The derivative right here, let's look at the first derivative. Let's look at it the way I've got in parentheses. Put in 1 in place of x there. 5 times 1 is 5, minus 7 is negative 2. So I get negative 5 over 2 ln of 5. That's the slope of the tangent line, which goes out here out front. Then we have x minus 1, and then we have the y value ln of 2 over ln of 5. So the tangent line and the original function both go through the point 1 comma ln of 2 over ln of 5. And the tangent line and the graph at the instantaneously has a slope negative 5 over 2 ln of 5. So if we graph the tangent line and the original graph together, we see the blue graph and the tangent line. Notice it crosses right here at when x is 1, and see y is ln of 2 over ln of 5. That's this point right there. And so we see both graphs are crossing there where they should, and crossing the same as this vertical line at x equals 1. And the tangent line is following the curve there, has the same slope. If we zoomed in close, they would look very much the same. Notice that the original function is defined everywhere because of this absolute value, except where the thing in here is 0. You notice you can never get a negative out of this because of the absolute value part here before you take the logarithm. But you could get a 0 here. So if x is 7/5, that's 1.4, then you're going to see a vertical asymptote right there. It's undefined. So this actually is kind of deceiving what it looks here. Here it actually goes down vertically right here, or nearly vertical, as it approaches that vertical tangent line. Notice what we see in the graph. We see that to the right here of the vertical asymptote, the original function is increasing concave up. And we see that its derivative, let's see, to the right of 7/5, this factor is positive and the rest of this is positive, so we see the derivative is positive up here above the x-axis, and the original function is increasing. We see this when we're to the right there, well, regardless of where we are actually, the second derivative is always negative. Notice the square here makes this positive, ln of 5 is positive, 25 is positive, but the negative out front makes the whole thing negative. So the second derivative, notice the green graph, is always below the x-axis. That means the original function is, it means the derivative function is decreasing everywhere it's defined, on this piece and on this piece separately. And the original function is concave down, both on this piece and this piece. To the left of the vertical asymptote at 7/5, the derivative, first derivative, is negative because that factor is negative. And so we see that the original, well, the red graph is below the x-axis to the left of the vertical asymptote, and the original function is decreasing. So that gives you a good look at that particular function. This is another one that's similar. You might want to use some properties of logarithms on this, my hint. The logarithm of the square root of the absolute value of 4x minus 7 over x cubed. See if you can work out the first and second derivatives of that and the tangent line when x equals 1 before you watch the next video.